Hey, I'm Aiden. In another class about computer vision, I learned about SIFT features and how to use those to make a panorama. So when I read through the assignment description, I saw the recommended method required the user to choose 4 index pairs. But since I had already made an autonomous script before, I wanted to try and see if I could recreate that in MATLAB. So I downloaded the computer vision toolbox and I got to work. First of all, panorama creation has 4 main parts: feature detection, feature matching, transformation creation, and alignment. Feature detection and matching are the parts omitted in the recommended method, but my code uses SIFT feature detection and MATLAB function match features to create index pairs. SIFT is scale invariant feature transform. Think of how to detect a feature. The most straightforward way is to look for copies of that pattern of pixels. However, what if that feature is larger or smaller in another image? How do you find it then? SIFT creates a pyramid of blurred images, similar to the Gaussian pyramids we used earlier. It runs feature detection on all of these. Instead of marking the pattern of pixels, it maps a dominant gradient direction for each. This way, if the feature is rotated or scaled, it can find it. SIFT also works best on black and white images, so I first convert images to grayscale. Now, after detecting features, the algorithm has to match them. Matches have different strengths, so we use a process called RANSAC, which stands for Random Sample Consensus, to pick the best matches. This model picks a random subset of points, follows a transformation that aligns those points, and then tests to see if all the other points in the equation follow this model. At the end, it keeps the best match. This process is important because SIFT will return bad matches. Think of like a railing. All of the bars look the same, so if any of them are detected as a feature, it can be matched to a different bar, which looks identical, but it would be a wrong match. However, every bad match is bad in its own unique way, while every good match follows the same good transformation. Thus, after enough iterations, you'll get a transformation that omits a majority of the bad matches. RANSAC returns index pairs, so we use those pairs with the function stgeoTform2D to estimate the geometric 2D transformation. Finally, we align and blend the 2 images accordingly. But before we can align, we have to pad the images. Assuming our image bank is sequential, we have to pad the first image on the right and the second image on the left, making a large enough canvas. Repeating this process yields a panorama. A challenge I ran into was that every time I passed the images in, the panorama would come out a different size each time, and this was because RANSAC was not running enough iterations. So I bumped the number from 2000 to 5000 so that the results would be more consistent. This is also important so I could crop out the black canvas accordingly in the output. Now, there are several shortcomings. Because I have to resize the images, otherwise it would time out, exceed the gigabyte limit, cause all sorts of other errors. Our matches are not as good as they could be. You can see artifacts in the MATLAB version that don't appear in Python's OpenCV version. In addition, because we align the right image to the other on the left, distortion is amplified the further right you go. You can see every image will kind of curve as the panorama extends right. With more time, I would try other feature detection and matching algorithms, such as Harris corner detector, to see how they compare. This method can also be improved with more computing power or more efficient use of memory so that you can detect higher resolution images. The more pixels, the better SIFT feature detection runs. Thanks for watching, and I hope you guys enjoyed seeing a different kind of panorama algorithm.